This is an introduction to biostatistics using R, and the lectures are going to just consist of me going through each of these chapters and sections, trying to create little 20-minute videos. And we'll start in on chapter 1. Just an introduction to biostatistics. And it really lays out the foundations necessary for much of the statistical nomenclature and the concepts, and we'll just go through one at a time. In introduction, briefly, there's two big categories of statistics. One is descriptive statistics, and it's just really meant to summarize and organize the data at hand. Okay, so what type of descriptive statistics? Usually it's measures of central tendency of some sort, and the most common ones are the mean, median, and mode. We're also measuring sources of variability or dispersion, how spread out the data are. And there's several measures that we'll cover in these videos: standard or variance, standard deviation, the min, the max of your data set, kurtosis, and skewness. And we also like to create frequency distributions or tables, graphs, charts. The next is inferential statistics, and it allows us to make predictions about the populations or generations about the population. So generally we don't collect every single observation from a population, but we take a sample, and then from that sample we make generalizations or predictions about the population. Okay, so we'll estimate population parameters. We use confidence intervals for this. So if we want to estimate the population mean, we can create a confidence interval, which is a range of values that we think that population parameter might fall in. Hypothesis tests. So that's where we're making specific claims about the population parameter, and then we can do hypothesis tests. Some common ones are t-tests and chi-square tests. Another inferential statistics is regression analysis, and that's where we take a set of variables to use to try to get a better estimate of some unknown quantity. So it's really examining the relationships between several variables. An analysis of variance, and the goal, it's always odd to me, and we'll talk more about this when we get into that video, but it's analysis of variance. And analysis, and of course ANOVA is the acronym that we use for that. But you would think that you're analyzing the variances somehow, or that's the goal, but it's not. The goal is to compare means. So we have the means between treatments or groups, and we want to, are they equal or is something different in there? And correlation is just measuring the strength of the relationship between variables. Now, some basic concepts, we have the data. What is the data? That's the collection of values that we have from our experiment or our sample observations that we're going to use to make an inference towards the population. But the data we collect can be numerical, which is called quantitative, or it can be categorical, which is called qualitative. And depending upon the type of data that we collect, kind of determines what type of analysis and descriptive statistics and et cetera that we use. Now in R, whenever you see the little R there, and then there is a shortcut name for some statistical distribution, that means that we're going to take a random sample from this distribution. So we're going to take a sample of size 10 from a normal distribution with a mean of 5 and a standard deviation of 1.5. We're going to store it in a variable x, and then let's print it out. And these are the 10 observations that we randomly obtained from this normal distribution with a mean of 5, standard deviation of 1.5. Now, to sample categorical variables, of course, there's, well, we'll leave it at that. And so here in R, that letter C stands for concatenate. So we're concatenating these values, and they happen to be character values, low, medium, and high. And we're putting them then in a vector. So this quantity here is, you think of it as a vector. And actually, whenever you're using the R statistical software, I think it helps to think of everything as a vector or a matrix of some sort of an array. And as we proceed through these videos, I'm going to highlight out that way of thinking. You know, if you can vectorize something, then it just makes it faster and it's a simpler way to think about it. So we have these vector values, low, medium, and high, and we're going to take samples from them with replacement, which means we're going to take one, look at it, record it, put it back, and then just repeat that process 10 times. Store it in the variable y, and then when we print it out, these are our observations. Now, statistics is, it's the science of collecting, analyzing, presenting, interpreting data. And it basically allows us to make inferences towards the population. That's the ultimate goal. Now, statistic in general is defined as a characteristic about your sample. Now, the sources of data that we can collect, and there's two ways to think about this, is one, we can prospectively collect data. So we set up an experiment and we observe something as time progresses. That's prospective. And that can be, from surveys, questionnaires, experiments, observations, record them in real time. We can interview people to collect data. And so, and those are, we are collecting them. So it's firsthand, it's prospective. And then there's, retrospective, or sometimes called observational, no, not observational studies, but, it already exists. And so it's a secondary data set. And so we can look at government reports, census data, journals, publications already. Maybe we're doing a meta-analysis from already published data, financial records, online databases, website. These are just a few of the examples. Now, biostatistics is a branch of statistics that deals with data relating to living organisms. It doesn't have to apply to clinical trials, although that's the world that I lived in for almost 3 decades. And that's where the stories I tell, or some of the examples, will lean towards. Now, a variable, very generically, it's something that you can measure. So it can be measured or categorized. And it represents an attribute that you can, take on different values across observations. And it's very generically. So if we want to look at the height of college students, then height is our variable. And then when we observe a student, then we can measure it, and that's what we've collected. So the variable is very generic. Now, yeah. But variables can be different types. There's quantitative, which means it represents a number. It's a numerical value. And within quantitative, there's 2 categories. Discrete, which means it can only take on a countable number of values, very distinct values. Now, that doesn't necessarily, here we create a random variable from a binomial distribution of size 10. The parameter for the binomial is n is 5 and p is 0.4. And this is our sample, so we're collecting integers. But a discrete variable doesn't have to be an integer. So if the only values that we can collect are 1.3, 1.5, 1.7, and 1.9, then it's discrete. So it's very distinct observations. It's numeric. It's countable. And a continuous variable, you think of it as over an interval or a range. Like height is technically, it can be anything within an interval, or temperature. And so here we're going to take a random sample from a gamma distribution, 10 observations, and then these are the parameters from that gamma distribution. And when we print them out, then we get this. Now, the other type of variable is called qualitative, and it really represents categorical variables or labels for that categorical variable. Now, nominal is probably the simplest form, and it's categories without a meaningful order, like gender or red, blue, green, things that don't have a natural ordering. And so here we're going to sample 3 colors. Remember, the C is for concatenating, so that's a vector of length 3. We're going to sample 1, replace it, and then keep doing this 10 times, and we're going to store these in here. So what we've stored is categorical variables in the variable x.cat. Now, when we go in later videos, we're going to use this in mathematical models or statistical models. And it doesn't, in the models, it doesn't know how to use green. So some way or somehow we're going to have to make that a numerical value of some sort so we can use it in models. And we'll talk more about this in later videos. But the factor command is the way that we tell R that, hey, it's a categorical variable, red, blue, and green, for instance, in this example. But if we use this variable, xcat, in a model, a statistical model, then we're going to create what are called dummy variables, indicator variables, or sometimes called hot one variables, when we use this data in our models. And anyway, it's a way that R knows how to use those in those models. So we're going to use factor quite a bit in this, and let's print them out, and we get these are the sampled values. Now, ordinal categorical variables are categories that have a meaningful order. Rankings of teams have a meaningful order. Rank 1, 2, 3. So those are categories, but it looks like we're using a number, but it's not. It's a ranking, or satisfaction levels. Here's a simple one that if we use low, medium, and high as our categorical labels, then we take a sample of size 10 from those. And here we use the factor, which is R's way of saying, hey, if we use this in a statistical model, then handle it in a very specific way. That's what this factor tells us. But here we're adding on this additional argument called ordered true. And then we have to provide the levels of that ordering. And then not only does it keep track of our sample that we obtained, so high, low, high, the order that we obtained them, but it also is keeping additional information of the ordering of those values. Okay. Now, a random variable. So remember, a variable is some sort of characteristic that we're interested in. But a random variable means we don't know its value until we conduct our experiment. Yeah, that's kind of the generic of it. It's a random variable. But in that definition will be okay when you're first learning statistics, but technically a random variable, it's a mathematical function that assigns a numerical value to the outcome of the experiment. And so, for example, if we're rolling a die and we want to observe the outcome of the top side, and write it down. We're counting the number of pips. So nothing in there is numerical. But when we roll a die and there's 3 of those little pips or dots on the top, then we create a mathematical function. Now, most of the time we don't realize we're doing it, but let's associate the number 3 with that outcome. And so in a random variable is technically it's the outcome, but we've assigned some sort of numerical value to it. If we're flipping a coin and we have heads and tails, so the random variable, flip a coin and observe the top side, that's our random variable, and we get heads and tails. But now to use that in mathematical models, somehow we have to convert that. So let's call a head a 1 and a tail a 0. Now the statistical population is, that's of course our primary interest. We take a sample from the population, we analyze the sample, study its characteristics, do hypothesis tests, and then we make an inference towards the population. Now, the statistical population is not always easy to think about in my mind. So you have to spend some time thinking about it. But it represents the entire group from which that we're collecting data from. So if I'm a surgeon at a hospital and I think I've invented a new method for kidney transplants, and I want to test if my method translates to better survival of the kidney, the recipient of the kidney, how would you conduct that study? Well, you're going to have to, have patients that first of all, need a kidney transplant, and they're willing to participate in your study. And so your study might consist of, give them the standard of care versus maybe this new method that you think is better, which meaning the survival of the patient will last longer. So what's your population? It's not all recipients of kidneys. It's patients that need a kidney, that live in your area, that go to your hospital, that want to participate in the study. And so your population is much narrower than the general population of that you want to this to be applied to. Anyway, but as we progress through here, we'll talk more about that. So you have to define the scope. It must clearly be specified. Is your population finite or infinite? Employees at a company may be finite, but all possible outcomes rolling a die would be infinite. And then, of course, there has to be sampling. How do you collect the sample? So we can't really study the entire population just because it's impractical. So we have to collect a sample. Well, how do we collect that sample? And that in itself can be that's also a big topic. Okay. So what is a sample? Samples, of course, is a subset of the larger population that's selected for analysis. Some key characteristics of the sample, of course, we want it representative, meaning we want it to be well chosen that reflects characteristics of the population. We have, is it a random sample or a non-random sample? Now, whenever possible, and you don't have to do this all the time. You can have non-random samples that create great science. But in general, randomness reduces bias in whether it's known or unknown. And of course, the larger the sample, then we tend to, it provides more reliable estimates of parameters. And I always tell people, everyone has used statistics at some point before you've even taken a statistics course. Let's say you're cooking macaroni, for macaroni and cheese, and you heat up your water, you put your noodles in, you wait so many minutes. How do you know that it's done? Well, you sample it. You take one noodle and you bite into it, and if that noodle is ready, you think that that one noodle, that sample size of one, is representative of your larger population, then you stop cooking or you don't stop cooking. And so we've all used sampling methods. Now, types of samples is we have simple random sampling, and that's where every member in the population has an equal chance of being selected. Here's a simple example. Let's say we have a population of size 200, and we can number each observation from 1 to 200. And so this would represent the population. And so we take a sample of size 10 from our population. We don't want to replace them because we want that observation for study. And then these are the observations that we've randomly picked. Okay. We have what's called stratified sampling. And so we divide a population into subgroups. And then within each subgroup, we take a small sample. Okay, so here I create this example where we're looking at elementary schools in your state. So in this made up example, we assume every school has 20 subjects. Maybe we're looking at first graders. And so I label students 1 through 20 at school 1, and then 1 through 20 at school 2, 1 through 20 at school, 10. I think we use 10 schools. And then I provide everyone a unique ID. So there's 200 students total. So what we do is within each school, so school 1, we randomly pick some. Within school 2, we randomly pick some. Within school 3, we randomly pick some. And this can be nice because that we get a little bit from every school, and we're not biased and say if we take school samples from students in the southern part of the state versus the northern part of the state. We're just sampling all of them. And you can look at your data. Head provides the first 6. Tail provides the last 6 observations. And here, they make software to do this, right? And in practice, that's what you should use. But in these videos, we're going to try to do everything from first principles and hopefully get you a better understanding of the procedure and just how R works in the R programming. So here we're going to use the function aggregate, and this is our data. So we put in the 200 IDs, and then this is our strata variable. So it's the schools. So there's 10 different schools. And then what it does is within each of these, so when it equals 1, then we only have the data from school 1, and then we use this function. And so we're going to sample 2 observations from school 1. Then it goes to school 2, and then only it restricts the data to school 2, and then it takes a sample. Now, and then it repeats it for all these strata, and then we store it in temp, and then I just print out the students that we sample. Now, in usually aggregate, I use for like the mean. So if this is a set of data, and then we have stratum, and then within each stratum, we calculate the mean. So we find the mean value within stratum. But this is stratified sampling. And so these would be our observation. Now, cluster sampling is very similar to stratified random sampling, but the groups we call clusters, and the clusters are randomly picked. So we don't pick every school in the state of Missouri. We just randomly pick clusters, and then we use every observation within that cluster. So here, there's 10 schools, 10 different schools, and we want to randomly pick 3 of them. And then these would be our 3. And then we grab every student from these 3 schools. And so that's what the subset does. This is all our data, and we're subsetting it based upon these 3 observations. Instead of printing out 60 observations, I just use the dim function, which tells us that there's 60 observations and 3 variables. Now, convenience sampling. Now, you might think, would we ever use convenience sampling? I would say if you're in clinical trials research, this is probably going to be the biggest used, sampling method. And if we go back to the surgeon that's looking at a new technique for kidney transplants, they use convenience sampling. They wait for the next patient to come in that needs a transplant and willing to participate in the protocol. And then the patient after that, it's unquestionably a convenience sampling. Okay. And it's based upon ease. Now, convenience samplings can introduce biases, of course, so you have to be careful. Now, usually one way to get around this is that we'll introduce randomization somehow. So we convenience sample patient 1, but then we randomly assign them to, say, the control group or the standard of care versus the treatment. That assignment is unknown. So there is sort of a randomness involved. But more on that later. Okay, so it's 27 minutes, so I'm going to stop it here, and we'll pick it up with measurement scales in the next video.